The trapezium rule then. Here's a picture of a function, y equals f(x), and we've got these intervals here, x0, x3, these x subdivided out intervals up to xn. So there's n intervals here, each of a distance h. Starting from A and finishing at B, these are the corresponding y values, and we can form trapeziums if we just put this line squared here. And depending on whether the curve is convex or concave, will determine whether the line is above or below. And it's an approximation to the area of the curve. So this area would be a half, because it's a trapezium, of the two heights, y0 plus y1, half base times height. So half base times height. Half of the average height here times the base is the area of the trapezium. Then the next one would be a half, and then it would be y1 plus y2. Lots of h, and it would be all the way down to the last one, which would be a half of yn minus 1 plus yn times h. So the half h would come outside a bracket. You'd have the first and the last one here and here that you could combine, and then everything else doubles up, doesn't it? See, there's two of those when the adjoining end of this side bracket equals the beginning of this side bracket. So all the internal y values here, from here through to n minus 1, there's two of them because they're counted twice. And this is the formula we have then. So let's use that formula and work out an area. So supposing we got these x and y values. So what's the area? Well, what's h? H is the distance across the intervals here. So it's 10 over 2. The first and the last, 2 plus 3 is 5, plus 2 lots of everything in between, 7 and 10, 15 and 17, 14 and 12, and the 6. 2 of all those. We've added the first and the last together in one fell swoop, the 2 and the 3 to make 5. So what do we get here? We get 5 lots of 5 plus 17, 34, 44, 49, 59, 63, 65, 75, 81. 2 lots of 81 is 162. So we get 162 plus 5 is 167 times 5, which is half of 1670, which is 835. 835 units measure of area, so it'd be units squared. If it was in meters, it would be meters squared, as in this example. Okay, one thing we wanted to mention was if we were thinking about a convex curve, the trapezium would be an underestimate. If we're thinking about a concave curve, the trapezium would be an overestimate. So depending on the shape of the curve, we'll often get an underestimate or an overestimate. But here, if we had more intervals, we'd get a more accurate fit, because we could just have this smaller section here, and here we'd have the smaller segments here divided out. So the more intervals we have, the more accurate the answer will be. Okay, so let's look at this next example now. Using trapezium with 4 strips between 0 and 0.8. 4 strips is 5 points, so it's 0.2, isn't it? Divide that by 4. 0.8, so that's 1 strip, 2 strips, 3 strips, 4 strips, so there's 5 ordinates on the x ordinate. And the y ordinates, well, it would be e to the 0 squared, minus 0 squared is 0, which is 1. Then we've got e to the minus 0.2 squared, e to the minus 0.4 squared, and e to the minus 0.6 squared, e to the minus 0.8 squared. So if we tap that in, that would be 0.04. Although we could leave it like that, couldn't we? Okay, good. So that would be, so the area then would be h over 2, the distance across the interval. Distance is 0.2 over 2, isn't it? The first and the last, so this one and this one, 1 plus e to the minus 0.82 plus 2 times all the ordinates in between. So that'd be e to the minus 0.2 squared plus e to the minus 0.4 squared plus e to the minus 0.6 squared. And we're working that out to 4 strips. Okay, using 4 strips. And we give the answer to 3 decimal places is what we're told in the question. Okay, let's work this out then. So I've got 0.2 over 2, which is 0.1. So I might as well put that in straight away, times bracket 1 plus e, which is here, to the minus 0.8 squared. E to the minus, and then it's 0.8 squared. Okay, plus 2 times bracket. Remember what that is now? Move this over here so we can see it. E to the minus 2 minus 0.2 squared plus e to the minus 0.4 squared. Okay, plus e to the minus 0.6 squared. Close the 2 times bracket and close the bracket at the end of the problem. Equals 0.654, and that would be 655 to 3 decimal places, wouldn't it? 0.655, and that's to 3 decimal places. Okay, good. Next problem now. So I've done that one. So the next problem is evaluate this example 3 to 3D. Okay, here with 2 strips and 4 strips. So let's move this out of the way. We'll do this another time. Put that down the bottom for now. Okay, we want to evaluate this integral to 3 decimal places using 2 strips or 4 strips. Let's just get rid of that answer now for the previous problem. Here's our new problem. So 2 strips, so that'd be 3 ordinates, so 0, 2 and 4, wouldn't it? So the distance h would be 2, 0, 2 and 4. So there's our strips, isn't it, so to speak, if you were thinking about it like that. And then we got 2 strips, 3 ordinates at 0, 2 and 4. So the x values would be x equals 0, 2 and 4. The y value would be square root of 0. Square root of 4 is 2 and square root of 2 is root 2. So area then for the first problem, h over 2, so it's 2 over 2. The first plus the last, 0 plus 2 is 2, plus 2 times the one that's in between. There's only one ordinate in between, 2 lots of that. So we get 2 plus 2 root 2, because that's a 1 there. We're working out to 3dp. So it's 2 plus 2 times the square root of 2. 4.828. That's the 3 decimal places. Okay, next one. We're going to do 4 strips. So we'll have a strip here and a strip here. Oops, there. Put it more accurately in this little sketch. So it's at 1, 2, 3 and 4. Gives us 4 strips, 5 ordinates. So the x's is 0, 1, 2, 3 and 4. The y value of root x is root 0 is 0, root 4 is 2, root 1 is 1, this is root 2 and this is root 3. These are the y values. So the area then, h, which is 1 over 2. The first plus the last are the y values. This one and this one is 2, plus 2 times the ones in between, which are these and this one. Those are the in-between values for y. So what do we get? We get... Okay, let's type it in the calculator then. We get 0.5 times bracket 2 plus 2 times bracket 1 plus square root of 2 plus the square root of 3. Close that 2 times bracket, close the bracket at the end. Oops, let's get outside the square root. There we go. 5.146 to 3D. Which would be a much more accurate answer, wouldn't it? 3 decimal places. Now we want to work out the error for these strips, so we'll work out the integral then. So here, the integral I, we can work it out exactly actually. X to the half is equal to x to the 3 over 2, over 3 over 2, raised to the power by 1 divided by that number, between 0 and 4, which is equal to, move the 2 up, x to the 3 over 2, over 3. Top value, take bottom. The bottom value will be 0. The top value, which is 4. 4 square rooted is 2, and then 2 cubed is 8. So it's 2 times 8 over 3, 16 over 3, which is 5.33, isn't it? 5.3 recurring units squared. So now we can work out the error term to 3D. For the first one, when we take it away, the first error term will be 0.505 if you want to tap that out in the calculator. So that's the first error term. The second error term here will be the difference between this and this, which is 0.187 to 3D. So it's just for reference, it's only a simple calculation there. Now we'll look at our final example. Estimate this to 2 decimal places. We'll do a little bit of it if we get time. Hopefully we might do a bit more, but we'll see. So let's have a go at it. Okay, here's the question then. Estimate this integral to 2 decimal places using the trapezium rule. And I've written down all the calculations here. So if we had 2 intervals, we'd have the 4.83, which is what I think we did with the 2 strips. We did that one. And we also worked out the 4 intervals. We got 5.15 near to 2dp. And that's the previous problems here. So if you do it to 8, 16, 32 and 64, you get these values coming out of the calculations. Now you'll notice that the values settle down to 2dp here, to 5.33. So that tells us this level of accuracy produces a stable result. So we can conclude that to 2dp, because of these results here, we can conclude that this is equal to 5.33 to 2dp, because anything accurate on 128 will also give us a 5.33 again.